All right, today we're going to crack the code on cryptography. It's the invisible shield that protects pretty much everything you do online. It's the real unsung hero of the internet, and we're about to pull back the curtain and see exactly how it all works. So, it all starts with something you've seen a million times but maybe never really thought about. That little S in HTTPS. What's it even for? Well, it stands for secure, and that one single letter, that S, represents an entire universe of technology that's designed to keep your digital life private and safe. But, to really get why we need that S, we first have to understand the internet's biggest, most fundamental problem. At its core, the internet wasn't really built for privacy. Just think of it like a giant public square or a busy highway. All of your data, your messages, your passwords, they're all traveling out in the open. And that means anyone can potentially listen in using a technique called packet sniffing. And here's the really scary part. Because it's a passive attack, they're just listening, not sending anything, it's incredibly hard to even know it's happening. That's why we can't just cross our fingers and hope for privacy. We have to build it in from the ground up. And that, right there, is where cryptography becomes absolutely crucial. So, the first huge breakthrough in solving this trust problem came way back in the 1970s, and it was a totally radical idea. See, for centuries, encryption always meant you had one secret key to lock the message and the same key to unlock it. But then someone asked, what if instead of one key, you had two? And that idea is what we now call asymmetric cryptography, or public key cryptography. And the main principle is actually pretty simple, but it's brilliant. Whatever one key locks, only its matched partner can unlock. This solved a massive problem. How do you safely share a secret key in the first place? This idea completely changed the game. Okay, the best way to wrap your head around this is to think about a mailbox. Your public key is like the mail slot. It's out there for the whole world to see. Anyone, your friend, your bank, an online store, can use that slot to drop a locked message into your mailbox. But only you have the private key. That's the actual key to the mailbox. You're the only one who can open it up and read what's inside. Now, this isn't just some clever trick. It's all based on some really tough math. The security of systems like RSA, for example, relies on a simple fact. It's super easy for a computer to multiply two massive prime numbers together. But it's almost impossible for even the most powerful computers to take that giant result and figure out what the original two primes were. That's the mathematical one-way street that keeps your data safe. So, how does your browser actually use this two-key magic to talk securely to a website? It all happens at a flash, in a process we call the TLS handshake. This is the secure part of HTTPS that we were talking about. And this happens so fast you don't even notice it. It's like a secret agent handshake. Your browser says, hey, website, prove you are who you say you are. The server sends back its credentials, its public key, all wrapped up in a signed digital certificate. Your browser checks it, gives it the thumbs up, and then they use that public key to secretly create a brand new temporary key that's only good for this one conversation. Now, that two-key system is amazing for starting the conversation and establishing trust. But here's the catch. It's a little bit slow for encrypting tons and tons of data. So once that handshake is done, the browser and the server switch over to a faster, more efficient method to actually scramble all the data they're sending back and forth. But even with that new secret key, there's another puzzle to solve. If you use a simple code, every time you encrypt the word hello, you'll get the same encrypted output, like X1, Y2. An attacker could easily spot these repeating patterns, and patterns are the absolute enemy of good encryption. So we have to find a way to introduce some randomness. And the solution is this really clever technique called cipher block chaining, or CBC. The core idea is to stop encrypting each little chunk of your message all by itself. Instead, you create a chain, where the encryption of one piece is completely dependent on the piece that came right before it. This dependency just obliterates any patterns. So check this out. You start with a random, unpredictable piece of data. You mix that with the first part of your message, and then you encrypt it. But here's the magic part. You take that scrambled result and you mix it in with the next chunk of your message before you encrypt that. Each piece now affects the next, creating this chain reaction. The result? Even if you send the word hello 100 times, it will look like a completely different random mess every single time. Okay, so we've got secrecy covered. Our messages are private, but that's only half the battle, right? What about authenticity? How can you be sure that an email really came from your boss? And how do you know it hasn't been changed along the way? This is where we use something called a digital signature. And this is where we take that whole two-key system and just flip it on its head. See, a signature isn't about hiding a message. It's about creating something that only you could have possibly created, but that anybody can check and verify. It's like a digital seal of authenticity. So here's how it works. You take your message and you create a unique digital fingerprint of it using a hash function. Then you encrypt that tiny fingerprint, but this time you use your private key. And since you're the only person on the planet with your private key, you're the only one who could have possibly created this signature. So to verify it, the person who gets your message uses your public key to unlock the signature, revealing the original fingerprint. Then they take the message they received and create a brand new fingerprint from it. And now, for the moment of truth, they compare the two. If those two fingerprints match perfectly, boom, they know two things for certain. The message is from you, and it hasn't been altered by one single bit. So why does all this matter? Well, this invisible cryptographic dance is happening constantly, all around you. It's the fundamental tech that lets us build trust on the internet, which, by its nature, is a totally untrustworthy place. I mean, every single time you buy something online, send a private message on an app, check your bank account, or even just get a software update for your phone, you are relying on these exact principles. The two keys establish trust. A temporary key provides fast encryption, and digital signatures guarantee authenticity. It is literally everywhere. And that leads to this great quote from Vinton Cerf, who's one of the pioneers of the internet. He said, "Don't be constrained by today's technology. Reach out and imagine what could be, and then make it happen." And that's really a perfect description of what happened here. The people who created these tools, they imagined a solution to what seemed like an impossible problem. And that brings us to the final, really crucial thought I want to leave you with. The security we rely on today, it's all based on math problems that are just too hard for our current computers to solve. But what happens when our computers get 1,000,000 times faster? What about quantum computing? It threatens to make these impossible problems totally trivial, breaking the very locks that protect our entire digital world. The next great cryptographic challenge isn't some far-off future idea. It's already here. The race is on to build security for a quantum future.